Okay, so let's look at a way that we can do the Boolean and retrieval mechanism in a more efficient manner. Uh, this comes from Andrew Kane's PhD thesis. This is where I've grabbed it from. Um, so the basic idea to speed things up is to intersect the postings from shortest to longest. So again, let's say we had 4 words in our query. So these are the postings for each of them, and we'll order them by their length from the shortest to the longest. And of course, since we've simply put the postings in an array, we easily know their size. And so we intersect the shortest one with the next one that's longer in length. And we're going to get some result set here. Then we intersect those to get this result set that we intersect together here to give us our final result. And so it just keeps going and going and going. So that's a nice way to see it. And I've kind of tried to visually show that, yeah, likely our result size is probably getting smaller and smaller as we go along, because it's less and less likely that we'll find documents that have all of the words. The nice thing about this is that the shortest length posting tells us right away, oh, this is the maximum possible set of documents that could satisfy this result set. It can't be any larger than that because, again, the Boolean and is it must be present. All the words must be present. So these are the documents that have one word, the most rare word in the query. So you have to have this word. Well, all right, maybe you also have these, and maybe you also have these and these, but you have to have these. So this is the maximum possible set of documents. If it either stays the same or it gets smaller as we do more and more intersections. What's the great advantage to this? Well, let's look at the pseudocode here for this. So again, we're going to pass in the smaller and then the larger one. That's what we mean. The size of m is less than or equal to the size of n. So we'll set an iterator into n. Okay, and so like imagine that this is just in the abstract, we're intersecting lists of numbers. Okay, and so you're going to end up initially with some iterator that's sitting here and pointing to the first element. So you're all ready to go. You set this guy to 0, you set your result set to the empty set, and now we're going to go through all the elements of our shortest list. And we ask this iterator, all right, race ahead and tell me if you've got this thing in your list. And so imagine the first one was, the value 8. Okay, well, we go here, we go, oh, I'm looking at a 3. Well, that's not it. I have these in sorted order. So, okay, I'll go ahead and I'll move myself as the iterator. I'll move myself forward looking for an 8. Ooh, I hit a 9. I'm going to stop there. I know I didn't have an 8 in my list, and so then I will go and I'll like return nil or null or something. And oh, well, that's not what m is equal to. So it's not in the list, so we're not going to add it to the result set because it's not found in both of these lists. Then we continue our loop back. We'll take the next thing, and maybe the next thing is a 9. And we go and we check, oh, we've got it. Nothing to do. We return the 9. Oh, we have a 9. We add it to the result set. All right, we go in here, and then, oh, maybe the next thing is, 60. Oh, so this guy races on ahead until, boom, now it hits the 63. Nope, I don't have a 60. And so it doesn't do that. So basically what ends up happening is we do very little changes to the result set, okay? What we end up doing is spending most of our time just simply racing on down these lists, skipping over things. So the computation largely ends up being taking an index and racing through each of these lists. So it ends up being this very fast linear search down these things. Now, it doesn't have to be a linear search. These are actually in sorted order. It's potential that it could be a lot faster, that we could, given where we are, we could do a binary search very quickly and determine whether or not we have it, and then set our index there. And so we could potentially race through these things really fast. Oh, we have to pause and stop basically whenever we're inserting things that, it's a little bit extra cost to insert something in. All right, well, other than that, it's basically let's race through these. Compare that to the naive approach I showed in the previous video, where, yeah, we're gonna go through and we're gonna make all these counts and comparisons and this and that. Oh, this is just largely like, let's go quickly through this, searching for the smallest number of things in the resulting set. So it ends up, we could do these as a bunch of binary searches to do these intersections, and this could run really fast. So you might like to actually see something that's a little bit closer to your own postings list rather than this abstract sense of how to intersect two lists if you wanted to use this sort of approach or try it. And for this, I have some code that comes from, there's a information retrieval textbook by Christopher Manning. So the source of this, ooh, that just went dry on me. So the source of this is the Christopher Manning IR textbook, information retrieval textbook. So it's pretty easy. Search into Google, just look for Manning information retrieval. This is all available online, by the way, so you can read that whole textbook for free. So in Manning, they provide an algorithm to do an intersect between two lists, P1 and P2. Okay, and so let's just say that these happen to be, I'm going to pass in initially, and maybe I've modified this, I actually can't remember, but let's say these are in arrays of postings. And again, this is where we've gone and we've packed into the array something that has the document ID and then the count. And we keep repeating this. It's document and then the count and so forth and so on. All right. So here we go. We're going to take these in. And again, we're pseudocode. This is for illustration purposes. You'd, of course, probably want to modify this. And so we'll start off with, let's let answer be an empty list. And in fact, we could actually set up answer to be, I'm going to show you that the result here is, oh, we've got the intersection. What you might really want to do is construct answer to have the same format as a postings list, but you don't need the counts in there. So you could just document space document, you could just, leave it as the default integer, which would be a 0. Anyway, let's not get into let's not worry about that. Let's look at this and run through it. I0, we'll also set j to 0. These are going to be our two indexes into the two lists. And we basically say while I is not equal to p1.length and j is not equal to p2.length. Okay, basically, we're going to run this until one of them hits the end of their list. If what we see P1I is equal to what's at P2 of J, then we know that they're in both lists. Okay, so we'll just add that to our answer. And by the way, if you wanted your resulting answer to have the same format, after you add the document ID here, just go ahead and add another 0. That would solve that. All right. So else, oh, sorry. Then we need in here, now that we found it, we need to advance both of those indexes. So j is equal to j plus 2, I is equal to I plus 2. That's the plus 2 is to skip over the count. All right. Else, if what we find is that the P1 of I is less than P2 of j, well, so our index into P1 is smaller, so we need to move P1 forward. So we go I is equal to I plus 2. Otherwise, the case is that P2 is smaller than P1, and so we need to move the J index forward. All right, so else J is equal to J plus 2. And when we've ripped through these guys, then we will be done, and we will be able to simply return our answer, which is the intersection. Okay, and so you could modify something like this to be able to allow you to intersect the first 2 lists, then the result, and then third list, and then the result and the 4th list, or whatever, until you're on done. And if you ordered them in the order from smallest to largest, okay, that would go pretty fast. Note that this here is doing linear searches. This is not doing a binary search in those lists. But do note that it does require them to be in sorted order, okay? So this idea of advancing down the lists, again, relies upon the postings being sorted in order of document ID. The great thing is that when we build our inverted index and we build these postings, that's what we do, is because we process the documents in order, and we number them then in order, and as we find the terms, we append to the posting list, so we end up with posting lists that are ordered by document ID. So they're already in the proper sorted order for that. All right, so that covers a better approach to doing Boolean and retrieval. Should be more efficient, maybe cleaner than the naive approach. Perhaps a little bit more complex for some people to implement. Nevertheless, do we really care about Boolean and retrieval? Well, as a retrieval method on its own, the answer is no. It's not a good retrieval method. So when we're going to end up comparing it to better ranking methods, we're going to find that it does not perform very well. It doesn't help the user very well to find material that the user finds is relevant. On the other hand, let's think about what happens when we go to something the size of the web, where we have billions of web pages. So we have billions of web pages. Well, and users are typing in these short queries of, maybe 2, 3 words, maybe sometimes 4. Well, given the huge amount of documents out there, we could get a really good pool of documents from which to do a better calculation of what is likely to be relevant to the user if we just say, oh, give me all the documents that contain all of the user's terms. And because there are so many documents out there, those are probably some of the really best documents because they have every single word in it that the user thought should be in there. Now, it doesn't work to do this, and then so in other words, you could then run a Boolean and fast, because Boolean and is fast, and find that set of documents, and then from that set of documents, then you could apply a more sophisticated ranking algorithm to actually rank those and show the ones that are more likely, hopefully more likely to the user to be relevant near the top. So in other words, use it sort of as a fast way to reduce the collection size to an even smaller size, and then run a more sophisticated ranking algorithm which is computationally more expensive, but it would only have to operate over a fewer number of documents. And so that sort of thing is absolutely a potential thing that web search engines can make use of. Are we going to use it? Does it work for these smaller collections? No. The Boolean AND will, one, often eliminate lots of potentially good documents because it demands that all the query terms be in the document, and we can have relevant documents that don't have every single query term in them. Likewise, it doesn't provide a ranking. It doesn't help at all. It just gives a set of potential documents. It doesn't say, well, maybe this one should be first and then this one second. It's just, here's the whole set. And that's really unfortunate because the user then has to go through them with no sort of better mechanism than, the ranking doesn't mean anything to the user. It's just a set. Anyways, so Boolean AND retrieval is not on its own a good retrieval mechanism. It may find utility in web search for reducing the set of documents for a more expensive ranker to run over. All right.